What does a black hole contain? Despicable fate of crushing? Openings to alternate realities? Multidimensional libraries? Weird ones? You may be in luck if you've always wondered, because some scientists have theorized that you are currently within a black hole. The general theory of relativity developed by Einstein has never failed. But in the centers of black holes and the Big Bang, we know it must. In both cases, matter is packed to infinite densities. These are singularities where general relativity fails to hold. It turns out that Einstein is not the only one who finds similarities between black holes and the Big Bang. Because of their mathematical resemblance to one another, some scientists think that the Big Bang is actually the singularity of an extremely massive black hole. Let's examine the degree of absurdity of this proposal. Let's start with black holes. Any sufficiently large collapsed piece of stuff becomes trapped by its own gravity. That appears to be an event horizon-encircled point of infinite density in general relativity. The surface where space itself flows like a river at the speed of light is known as the event horizon. Nothing can resist that current. Because nothing, not even light, can escape from below the event horizon, the black hole appears to the outside world as an orb of blackness at a certain point in space. There are also singularities and event horizons in the universe. The Big Bang, which we conceptualize as the moment in the early cosmos when all matter was compressed to an infinite density and all points in space overlapped, is the singularity. Space has expanded since the Big Bang and is still expanding. Our event horizon is derived from that expansion. There must be remote parts of the cosmos that are being accelerated beyond the speed of light if space is expanding uniformly everywhere. As a result, there exists a surface at a specific distance that serves as the boundary of our observational range, beyond which we are unable to learn about any event. The cosmic event horizon is seen here. It's a little more complicated today. For instance, because the light came from the objects before they passed the horizon, we can still get light from those that are now beyond it. Furthermore, the cosmological event horizon is nearer to us than the point at which recession equals the speed of light due to the universe's accelerated expansion. However, the outcome is the same. Nothing that occurs beyond that horizon today can ever be seen. Notwithstanding their differences, the universe and black holes have a lot in common. The Big Bang singularity is a time of infinite density that encompassed all of space, but the black hole singularity appears to us to be a point of infinite density in space. This is the clear distinction. It turns out that the difference isn't as great as it seems. The Big Bang singularity and the black hole singularity both occupy all of space. The only distinction is that the former exists for all of space in the past, whilst the latter exists for all of black hole space in the future. Alright, so that last bit definitely need a bit more clarification. Geodesic incompleteness is a concept that we have discussed in a few episodes, including our most recent one regarding the universe's center and the one where we discussed what happened before the Big Bang. Here's a reminder on that concept in case you need it. According to general relativity, objects that are not subject to a force follow a path known as a geodesic. These are the straightest routes through a curved space-time that are possible. Geodesics can be thought of as the grid that defines space-time. The arc of a ball thrown through the air, for example, can be used to establish a geodesic at any location in space and time, and it can then be traced both forward and backward. The trajectory of the thrown ball will be defined by that trace, but you can also extrapolate beyond it. If the ball could travel through the planet, it would take that route. Alternatively, it may have traveled through the Earth and arrived at its current location. The geodesic is specified for all past and future times apart from the ball, thus you can continue following it into the indefinite future or all the way back to the Big Bang. In general, geodesics don't finish. Aside from singularity, in actuality, singularities are described as the ends of geodesics in general relativity. At the Great Bang, all of the universe's geodesics come to an end. Because the Big Bang occupies all of space in the past, we refer to it as a past, space-like singularity. There is a future, space-like singularity inside a black hole. It implies that the singularity in the future is when all geodesics inside a black hole space-time cease. No, that does not imply that a black hole will swallow you whole. You might, but you might not really. Similar to how the Big Bang is the all-encompassing past for the outer universe, the black hole singularity is the all-encompassing future for the space-time that exists underneath the event horizon. Thus, there is growing similarity between the singularities of the Big Bang and the black hole. Their residency in the future as opposed to the past is the distinction. Additionally, the reality that black holes are a part of a larger cosmos, the cosmos as a whole, is the Big Bang. How can a black hole be made to resemble the universe more closely? For someone to be within a black hole, we must make the interior of the hole mathematically identical to the universe. Sending that singularity to the past is the first step. Simple enough is a black hole with reverse time. It is a white hole and a legitimate solution to the equations of Einstein. Of course, we have already talked about them. An event horizon around the white hole's previous, space-like singularity can only be crossed from the inside to the outside, in contrast to the black hole's event horizon. From within, space travels over the event horizon at the speed of light. That's beginning to resemble our universe, a singularity in the past that resembles space and an impenetrable event horizon. However, there is still an outside where the white hole is seen as a bright, confined spot in space. The outside, which differs in its singularity origin. However, that would be unknown to everyone inside the white hole. Could they therefore be duped into believing they live in a normal universe? Despite these parallels, the white hole's interior does not initially resemble our universe. Now, the white hole was discovered by tampering with Carl Schwarzschild's original black hole solution's coordinates. By the way, this same approach gave us mirror universes and wormholes, which we mapped in an earlier episode. This kind of white holes inside is completely unlike anything in the cosmos. For starters, it is extremely inhomogeneous and composed entirely of space-time with no matter added. As you get closer to the singularity, the curvature changes significantly. However, matter and energy appear to be extremely equally distributed throughout our cosmos, and this distribution was even more uniform in the early beginning. There are also no extreme tidal forces, unlike in a white or black hole, because the space-time curvature is almost flat. The Friedmann-Lemaitre-Robertson-Walker metric, which we also discussed in the episode about the core of the universe, accurately characterizes the space-time of our universe. However, it is possible to put a FLRW metric into a black or white hole so that individuals inside cannot distinguish between the two. 1939 saw the discovery of the first realistic mathematical explanation of a black hole generation by renowned atomic bomb scientist Robert Oppenheimer and his pupil Hartland Snyder. By simulating a spherical cloud of matter with a completely homogeneous density and zero pressure, they were able to imitate the collapse of a star. The object falls under the force of its own gravity, forming an event horizon around it. Yet, the stuff inside the collapsing cloud is homogeneous and space-time is flat until it reaches a singularity. Nowadays, actual stars don't resemble this. They have a lot of pressure and become denser toward the center. However, the Oppenheimer-Snyder solution provided our initial understanding of how black holes emerge. It also displayed an additional strange trait. The FLRW metric is based on the same homogeneity and zero pressure assumptions that Alexander Friedmann used when he initially solved the Einstein equations for the entire universe. In actuality, you can patch FLRW metric inside a Schwarzschild metric to characterize the space-time of a collapsing star. And that remains the case even after the event horizon of the black hole arises. Thus, inside the still collapsing star, you can have what appears to be luxuriously flat space but is actually a black hole from the outside. It should function for the white hole if it does for the black hole. All it takes to create a white hole with an expanding space bubble that resembles our universe is to invert the time axis. A large enough white hole might resemble our universe precisely. In his black hole cosmology idea from 1972, Indian physicist Raj Pathria essentially put this out there. To the best of my knowledge, no one has provided a compelling argument demonstrating how this cannot be true. Another theory holds that white holes formed following a black hole's collapse give birth to universes. That's Lee Smolin's theory of cosmological natural selection, and yes, we did an episode. Under such circumstances, black holes do not develop singularities. Instead, they bounce back outward from the resulting white hole, which then forms additional black holes, etc., to build new space-times. Okay, so in order to respond maybe to our first query, are we in a black hole? We need one more component. Stephen Hawking demonstrated in 1999 that the distinction between a black hole and a white hole becomes hazy if the black hole is leaking mass via Hawking radiation in perfect equilibrium with the radiation it receives, such as from the cosmic microwave background. They might be the same thing. An indirect way to demonstrate that we might not be in a black hole is to combine the two concepts, Hawking's argument equating white holes with black holes and a very specific architecture for white holes that makes them appear like our universe from within. Hence, is the cosmos a black hole? Or a hole in the sky? Most likely not. However, not completely. Therefore, we shouldn't think that the cosmos is a black hole because there is no solid evidence to support this theory. To truly take this hypothesis seriously, it would need to have some deeper explanatory value. Although cosmological natural selection may be a route toward it, in order to move forward with it, we also need some supporting data. There is, however, a major benefit if we are within a black hole. We now know what the interior of a black hole looks like. This is how it seems. Yes, this black hole does contain libraries. Maybe one day one of those library books will also provide the answer to the following query. What is outside the event horizon of a black or white hole if we are inside it? Perhaps there is a universe where people ask the same question and receive the same response, that they are in a black hole, and so on and so forth in a chain of black holes, creating an infinitely nested space-time.